Welcome to Stats 2 students. Here's some holiday homework that I gave you. Hope you're having a little bit of a look at it. Here's my attempt at doing it. So these are the 2016 February March paper 7-2 questions that we should be able to do so far. So 1, a six-sided die is thrown 20 times and the number of sixes, X is recorded. Okay, number of sixes, X is recorded. Another fair six-sided die is thrown 20 times and the number of odd numbered scores, Y, is recorded. Find the mean and standard deviation of X plus Y. So with this question here, what I'm going to start off by doing is looking at the first one. X is binomial, isn't it? And you've got 20 trials and the chance of getting a sixth is 1/6 if it's fair. And therefore the expected value is going to be NP, so 20 over 6, right, 20 times 1/6 or 20 over 6, which is equal to 10 over 3. And then var X is NPQ, so number of trials times the probability of success times the probability of non-success. So that would be 20 times 1/6 times 5/6. And what do we get here? So that's like 100 over 36, isn't it? And then we can divide both of those by 4, top and bottom, so 25 over 9. Okay. Now we're going to do the same for Y, because what we're trying to find is we're trying to find E of X plus Y, and to find the standard deviation, we're trying to find var of X plus Y. So what I'm going to do is I'm going to work out what both of those individually are, then we're going to use our then we're going to put them together. So Y is also binomial. This time we're talking about, there's 20 trials. This time we're talking about the number of times we get odd numbered scores, and obviously there are half of the scores on the die are odd and half of them are even, so it's 20 1/2. And then we can use the same, oops, I'll just make this a bit smaller. EX is therefore going to be 20 times 1/2, which is obviously 10. And var X in this case will be 20 times NPQ, 20 times 1/2 times 1/2. So it will be 5. Hope that makes sense. And now we're ready to go. Linear combinations of variables. So E of X plus Y is simply going to be, we're going to add together this and this. So what are we going to get? We're going to get 10 plus 10 over 3, and that's going to give us 40 over 3. And then we can also do var X plus Y, and we're just going to again simply add the variances here. So we've got this one here and this one here. We add those two together. And this gives us 70 over 9. But of course, notice in the question it wants us to give the standard deviation. So therefore, the standard deviation equals the square root of 70 over 9. And we know that we can rewrite that to be equal to the square root of 70 over 3. And that will be all for that one. We've done that. So that's good. Okay. Let's go on to the second question. So here we have Jill shooting arrows at a target. Good on Jill. Last week, 65% of her shots hit the target. She's doing better than most. Okay, this, I was going to make a rude comment about a political party, but I decided not. 65% of her shots hit the target. This week, Jill claims she has improved. It does sound like politics, doesn't it? Out of her first 20 shots this week, she hits with 18. So we've got 20 shots, she hits 18. Assuming the shots are independent, test the claim at the 1% significance level. Okay, when you hear this kind of thing, you should be thinking hypothesis testing. Okay, and the reason you should be thinking that is because you've got a great teacher. No, it's because of this here and this, right? It's giving you big clues. Okay, so our null hypothesis, we're going to write this down. What is our null hypothesis? Our null hypothesis, since we're dealing with this, we can call this like a, we can call this like a binomial, so we'll go P proportion equals 0.65. That's what we're testing against. She reckons she's improved. So therefore, the alternative hypothesis is P is greater than 0.65. In other words, she thinks she hits it more than 65% of the time now because she's got better. Okay, question is, has she? Now, you can see that this is going to be one-tailed. A one-tailed test, isn't it? Because you're dealing with just a greater than, not an equal to. Okay, so that's what tells us it's a one-tailed test. Okay, and it's the 1% level. So one-tailed, and it means ruling out top 1% of this distribution. Okay, that's what we're doing. We're going to say anything in the top 1% is questionable whether it is part of this distribution with P equaling 0.65. Now, let's write out our distribution. It's a binomial distribution. There are 20 trials. The probability of success according to our null hypothesis is 0.65. And what we're going to do is look at, 18 shots, 19 and 20. That's the top part of this distribution. So we're going to see what 18 and above equals. So what's the probability that X is greater than or equal to 18? And when we do that, we're going to have to do 20, choose 18 times 0.65 to the 18 times 0.35 to the 2. And then plus 20, choose 19 times 0.65 to the 19 times 0.35 to the 1 plus 20, choose 20, which equals 1, so we didn't worry about it, 0.65 to the 20. We could ignore this last bit, but just so you see what's happening, we're going to 0.35 to the 0. Now, if we chuck this into our calculator, what do we get? Okay, I'm getting 0.0121. And once you get this result, so that's basically 18 and above is 1.21%. So you've got to compare it to the significance level. So we're going to go 0.0121. Now we can see that that's greater than 1%, isn't it? So it's greater than 0.01. And now we're going to draw a conclusion. Therefore, now because this means that 18 and above is more than 1%, it means that this could be in the distribution. We're not ruling it out. It's when it would be less than 1% that we know, oh, yep, that should be ruled out. So we're going to therefore accept H0 and say there is insufficient evidence to suggest she has improved at the 1% significance level. And I'd leave it there, and I think that's probably enough. Okay, what else have we got? Okay, the next one, the masses in grams of large bags of sugar and small bags of sugar are denoted by X and Y, and we've got them normally distributed like this, with the first number, of course, representing the mean, and the second number is the variance for each. And we're trying to find the probability that the mass of a randomly chosen bag, large bag, is less than twice the mass of a randomly chosen small bag. So in essence, what we're trying to see is that Y is less than 2X. Okay, so that's what we're trying to find. And the way we can do this is we're trying to find the probability that Y take away 2X is less than 0, right? In other words, you get a negative number because the Y is smaller than the two lots of X. So that's what we're in essence trying to do here. But we need to, what we want to do is make up this distribution. So how we do this, we'll go E Y minus 2X. So this is talking E here is our expected value, and so we're thinking about the mean here. So they're both normal, so it's going to be, this is also going to be normal, and to work out the expected value, we're going to take our Y expected value, which is 5.1, and then, well, I guess I should say mean, but 5.1, and then we're going to take away two lots of the X, which is 2.5. And so this gives us 0.1, doesn't it? And then the variance is going to be, so looking at this one, so it's going to be 0.2 squared. Now remember, we add the variances even though there's this minus here because variance is a squared thing. So plus 0.1 squared, which is the variance of Y, but also remember times 2 squared because we've got a 2 here, right? So that's 2 squared times 0.1. Now when we chuck this all together, what is that? I think it's 0.08, isn't it? 0.2 squared plus 0.1 squared times 4. Yeah, 0.08. 0.08. Okay, now once we've got to this point, we can now say that we've got Y minus 2X is normally distributed, and we've got 0.1 is our mean, and 0.08 is our variance. And now we can say the probability that Y minus 2X is less than 0 is equal to the probability, and we're going to use change it to standard normal distribution by using Z, is less than 0. Now we can put in our mean, 0, take away our mean, over our standard deviation, which is the square root of our variance. And we can see that that is equal to the probability that Z is less than negative 0.354, which is the same as 1 minus phi 0.354. So if you're a bit hazy on that, you want to go back to your PM1. Now, 0.354, I think I've actually got a, there we go, 0.54. 3, 5, 4. I think it's 6, 3, 6, 3, 8, 3, I think. Uh, 1 minus 0.6383. And that should give us, to three significant figures, 0.362. That's the 3SF. That's our final answer. Okay, so that's that one, dealt with that. Okay, I think we've got one more question. I'm making it quite a long video. But we'll do it anyway. Okay. The battery in Sue's phone runs out at random moments. Over a long period, she finds out that on average runs out 3.3 times in a 30-day period. This to me is sounding straight away like we've got Poisson distribution with lambda 3.3. Okay, that's what it sounds like to me. The probability the battery runs out fewer than 3 times in a 25-day period. Okay, so this is quite easy really. All we have to do for part 1 is we're going to change our Poisson distribution. You notice that this is 30 days and this is 25. So all we're going to need to do for lambda is we're going to take the original 3.3, which is for 30 days, and then we're going to times it by 25 over 30. Okay, so we're dividing by 30 to find what 1 day is, and then timesing by 25 to find out what 25 days is. So our distribution ends up being x is in the Poisson distribution and then 2.75. Right, and now we can find the probability. Probability that x is less than 3 for this one is going to be equal to e to the minus 2.75, so that's the lambda there, into 1 plus 2.75, that's 2, and then 1, 0, 1, and then we need 2, plus 2.75 squared over 2 factorial. And then we'll pop that into our calculator. We should get 0.481. So that's that one. Number 2. Use an approximating distribution. Okay, an approximating distribution. Okay, so straight away, because it's Poisson, we must be going to normal, I think, to find the probability the battery runs out more than 50 times. More than 50 times in a year, which is 365 days. Okay, so we need to change this to Poisson, from Poisson to normal distribution. Okay, so normal distribution is, well, first of all, we'll turn it into Poisson distribution. So if it's 365 days, we can take the original distribution, which is 3.3, and then we're going to times it by 365, which is 1 year, divided by 30. So we're going down to 1 day by dividing by 30. We're multiplying by 365 to find out what it will be in a year. So in this case, we've got a Poisson distribution of with lambda 40.15. Now, we can say this is approximately normal. So, with 40.15 for the mean and obviously 40.15 for the variance, because remember Poisson, the variance and the mean are the same. Okay, so we're going to approximate it with this. And then we're going to go, now what's the probability that x is more than 50? X is greater than. Now, because we're going from Poisson, which is not continuous, it's just discrete, right? I'm having a mind blank here, but we're going to continuous. So we're going to say greater than 50.5. So continuity correction going on here. And this should be equal to the probability that, now we're going to do the standard normal distribution, that z is greater than 50.5 subtract 40.15 over square root 40.15. And this is equal to the probability that z is greater than, and I think that works out, I got 1.633. And again, all we're going to need to do there is find that is equal to 1 minus phi 1.633. So let's have a look. 1.633. 1.63. I think this is 1.63. Let's have a look. Yep, 3, and then we've got to add 3 more to it, which is over here. So 9487. 9487. Equals 1 minus 0.9487, and when we do that, 1 minus 0.9487 gives us 0.0513. And the next one, justify the approximating distribution used. So lambda was greater than 15. I think that was the number that we had in our texts, I think. Now, part 3, independently of her phone battery, Sue's computer battery also runs out at random moments. On average, it runs out twice in a 15-day period. She's a bit unlucky with her tech. Find the probability of the total number of times the phone battery and a computer battery run out. Okay, so total number, phone and computer in a 10-day period. Okay, so we've got, let's say this is our, what is it, phone? Phone, yeah, the phone is X, and it's PO 3.3. And then let's say the computer is Y is, or is it computer battery? Yeah, Y is also Poisson, but it's 2. Now this here you see is 30 days, and this here is 15 days. We want both of them in a 10-day period. So to get this one to a 10-day period, we're just going to divide by 3. So we can say this is going to be 1.1. To get this one to a 10-day period, we're going to go y is Poisson, and we're going to go 2 times 10 over 15, or 2/3, which gives us y is Poisson. What's that? 1.3 recurring, or 4/3, right? Okay, so therefore x plus y, because this is the total number of times that they run out, is going to be also Poisson, and we add those two together, 1.1 plus 4 over 3, which ends up being 2.43 recurring. And we want to find the probability that x plus y is at least 4, so is greater than, whoops, I'm going to put that bracket there, is greater than or equal to 4. So we go 1, take away e to the negative 2.43 recurring into 1 plus 2.43 plus 2.43 squared over 2 factorial plus 2.43 cubed over 3 factorial. And we chuck this into a calculator, and we should be getting 0.228. All right, well that's a wrap on that one. It took a bit longer than I was hoping, 25 minutes. Let me know if you've got any questions. Happy to help.